All right, so let's begin this new unit. We're going to be talking about section 8.3 today, which is a section on something called polar coordinates. All right. And as you know, I really like to start with what we know, right? And think about all of the strengths that we bring to the classroom. And we're going to start with just plotting some points, okay? And so let's start with this point, 0, 0. I think we all feel good that this is right here at the origin. If we took a look at the green coordinate 2, 3, can someone just explain to me how we get to that point 2, 3? Like, how do we know where to plot it on our graph? Exactly. So Dallas says we're going to go to the right 2 and we're going to go up 3. And in particular, what about the 2, 3 tells us to go right 3? Like, how come we're not going to the left 3? Great, exactly. We have this 2 is a positive 2, which means we go to the right 2. And then this 3, similarly, is a positive 3, which means we go up 3. Right? And that might be something that we've known for so long that we're like, obviously, Judy, 2, 3 is going to be over 2 to the right and up 3, right? But just to make sure we really got that, if we wanted to plot negative 3, 1, we would go to the left 3 units and we would go up 1 unit and we would get to negative 3, 1. And last but not least, if we wanted to even plot like decimals, we could do that, right? It's a little bit less pretty, but in this example, we have negative 1.5, comma, negative 2.5. And so we would go to the left 1.5, and then we would go down 2.5 to get to our point, okay? Now, we actually have a name for this kind of coordinate system. In fact, we actually have 2 names for this. And one of the things that definitely is important as we move through mathematics is not just understanding the concept, but also the vocabulary that goes with it. And so over here, we're going to give this 2 names, all right? So one name you might hear is you might hear it called the rectangular coordinate system, right? But there's also another name for it that maybe we tend to hear a little bit less often, but I think moving forward, you'll start to hear a lot more. And that is Cartesian, okay? So when we see a grid that looks like this and we plot points the way we normally do, we call that rectangular or Cartesian coordinate system. And we have our X and Y as like our general form for that, right? But what's new today, which I think is pretty exciting, is we have something that looks like this, okay? And this, my friends, is something we call polar coordinates, okay? And we have a few sample points here, all right? So before we look at the sample points, let's kind of put these 2 side by side. And I'm wondering if folks can tell me one thing that they see that is the same about these 2, like the rectangular coordinates and the polar coordinates. What's the same about them?
They both have a center.
And they both have a center, right? And in fact, we do say, here we have an origin, here we have an origin. Great. All right. What's one thing that's different about our Cartesian coordinate versus our polar coordinate?
The radians.
Yeah, their radians is on a circle, right? So many things seem different. And so one of the things that I really like that we noticed here is instead of having sort of like an X, Y situation, we have these circles, all right? This is very poor tracing, but we have these circles, right? That's actually one part of the points that we're going to talk about. And then we also have these things that I think are familiar because they're kind of like the unit circle that we've been looking at, right? It's almost like we took our rectangular coordinate system and the unit circle and they had a baby. I would agree. I also saw that typo. I don't know why that is a pi over 3. It should 100% be pi over 2. Okay. All right. So before we write down sort of like what we have in terms of an XY for polar coordinates, I'm wondering if someone can tell me how they think whoever drew this got to the red dot, like 2 comma pi over 6. How did they get that to be right here? All right, I see one idea there, maybe the angle and then out 2 layers. All right, so when we see this angle pi over 6, so maybe that person was like, I'm going to go to pi over 6 on my unit circle. And then using Ellie's language of that center, right? If we have the center and now we go out 1, 2 circles, we get to 2 comma pi over 6. Right? So I think that's a pretty good idea. Let's see if it holds true for the purple coordinate and for the green coordinate. Okay. So given 2 comma pi and what Dallas suggested, where should we go first if we're looking to find where 2 comma pi is? Yeah, we're going to go to that angle first. So we go to pi, right? We go to pi. And then the 2 tells us from our center, we go out 2. Oh, that kind of paused a little bit. There we go. 2 circles or 2 layers. Okay. Let's check that with this green one. Green one, we would go to the angle first, 7 pi over 4. And from our center, we don't want to go out 2 circles. We want to go out 1, 2, 3. All right. So I think that's a pretty good observation there that maybe for polar coordinates, we go to our angle first, and then we count out how many circles, okay? And so with the polar coordinates, it turns out that instead of writing x comma y, we write r comma theta, okay? So r being how many circles we go out, and theta being what angle we go to. Okay. So if someone hands you a polar coordinate plane, you wouldn't say, oh, x comma y, but you would say, oh, r comma theta, right? I'm going to go to an angle first, and then I'm going to count out how many circles, right? And so that's the basic gist of what we're going to do in the first part of class today. We're going to play around with these polar coordinates, all right? And so let's go ahead and take a look at these, all right? Now, let me see how we want to do this. All right. So I know that folks are able to annotate on my screen. And so I wonder if anyone can just type in or say a quick reminder on how to do that. Like if you wanted to annotate on someone else's screen, how do you access that on Zoom? Don't all jump at once. Yeah, it's okay. I know it's not something I feel like last year students were like super excited to do this. And so we did it a lot, but I know we haven't done that this much in this class. On the view options, did I not change this? View options. Oh, maybe we can't do this with the new. Well, that's super sad. Okay, well, we can do it a less fun way then. All right. So what I wanted us to do is to be able to have a chance to sort of draw on the screen where these are, but that's neither here nor there. So if we wanted to, let's maybe focus on this graph in example 1. And I'm wondering if someone can tell me what I should do to plot point A. Right, let's keep track of. All right, so we'll do A, we'll do B. All right, so if I wanted to plot point A, wonderful, I would go to pi over 4. And then from the center, I would go out 3 circles, okay? So I find pi over 4, and from my center, I'm gonna count out 1, 2, 3. And so point A should be right here. Right? All right. Can I get someone else to tell me how I should plot point B?
We're gonna go to where pi over 2 is and go 2 circles out.
Perfect. So we find pi over 2. There's no typo on this one. And we're going to start from the center. We're going to count out 2 circles. So point B would be somewhere here. All right, great. Can I get someone else to tell me how to plot point C? Where do I go to find point C? Great, thanks, Matt. So we're gonna go to 4 pi over 3, which is down here in quadrant 3. We're gonna count out 4 units from the center, or 4 circles. So 1, 2, 3, 4, and this will give us point C. Wonderful, okay? So we're gonna do the angle first, and then we get to our how many circles out, okay? All right, so let's try the same thing with example 2. All right, and so let's zoom in on example 2 over here. Let's get some new colors going. So we've got point D over here. We've got point E over here. And what color have we not used yet? Like a reddish. Okay. So someone else who has not shared yet. How do we graph any of the points above? You can choose D, E, or F.
So for F, would you, so since it's negative 2 pi 3, instead of starting at like where the regular 2 pi 3 is, would you go to the negative of it like 4 pi 3?
That is exactly what you would do, okay? And so we have this negative 2 pi over 3 here. Thanks so much, Carrie. And so we don't want to go to this 2 pi over 3. We could go there first, but then we think about maybe that little trick where we do that and then we reflect it over the x-axis. And you're right, we would be looking for something, along the lines of 4 pi over 3. And we would go out 4 circles there. And so if we count, we get 1, 2, 3, 4 circles. And this would be point F, right? All right, let's see. Casey's got for 3 comma 9 pi over 4. Let me get back to the correct color. Then you go to pi over 4 and then do 3 out from the center. I would agree 100% with that. And so one way that you can do this is we can just sort of count how many pi over 4s, right? And so that's sort of a flashback to the first week or so of class. We have 1 pi over 4, 2 pi, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. 9 pi over 4 is going to be at the same place as pi over 4. All right. And it looks like, Ian, you've got that same idea here. And so maybe we'll write for ourselves, this is the same as 9 pi over 4. And then we're going to go out 1, 2, 3 circles and label that D. That's wonderful. Okay. And then last but not least, who has got E? E is an elephant. And I'd say that if you have like a gut instinct on how to do that, you're probably right for E. Okay, you're probably right. Yeah, exactly. So we're going to go to our angle first, just like we've been doing, right? We're going to go to pi over 2. But this time, instead of counting in the up direction to go 2 circles out, we're actually going to go down to represent that negative 2. And so we would end up over here. We could call that E as an elephant. Great. And I love the 2 different descriptions we have there. One saying it's in the direction of 3 pi over 2, and the other one saying we're going to go here, but then we're going to go in the negative direction. Okay, so both are valid ways of thinking about that. And so if I sort of go back and now we can look at both example 1 and example 2, I'm wondering if you can tell me one thing that you notice that is the same between example 1 and example
2. Oh wait, never mind. Sorry. The x coordinates are all whole numbers.
The x coordinates are all whole numbers. I agree with that. They're reflected about the origin. Tell me a little bit more about that. What do you mean by reflected about the origin? And maybe instead of comparing like a whole bunch of things, pick some that you're looking at specifically. Oh, Okay. All right, so you're saying that B and E are reflected about the origin, okay? Meaning like B is 2 up, whereas E is 2 down. I would agree with that. Okay. And so A and F, let's see. A is at pi over 4. If I reflected that about the origin, which angle would that land on? Yeah, 5 pi over 4, right? That would actually be somewhere along this line. Oh, so it's pretty close. I would say, yeah, it's pretty close, but it's not exactly a reflection. You're headed in the right direction. I really like what you're doing and looking at both sets of points to see if anything is the same. So great observation that B and E are reflections of each other. What can we say as we compare and contrast the other points like A and C with D and F? Oh, A and D are the same. Let's see. A is pi over 4 and 2, oh, sorry, 3 circles out. D, like Casey said, is also at pi over 4 and 3 units out. I would agree. A and D are exactly the same. Okay, well, let's take a look at the points for a moment. A, we called 3 comma pi over 4, but D, we called 3 comma 9 pi over 4. I didn't give you the same directions to get there, but you ended up at the same point. And so that's actually one of the neat things about polar coordinate is you can have more than one name for the same point. So I can say 3 comma pi over 4, and someone else can say 3 comma 9 pi over 4, and we'll end up at the same point. All right, think about it like if you are ever giving someone directions somewhere, right? You might be like, oh, okay, you're gonna go up to this street, and then you're gonna make a right, and then you're gonna make another right, and you'll get there. And someone else might be like, no, 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 you're gonna go left, and then another left, and then you'll end up there. And so 2 people are giving different sets of directions, but you end up at the same location. All right, so that's sort of one thing that's a little bit more powerful about polar coordinates. You can get to the same place using multiple types of directions. Okay, now it turns out that if we look at C and we look at F, we might also notice C and F are also the same point. Okay, and so let's get that over there. These are the same point. Right. So one way that you can say, oh, here's a different way to get there is you can have someone go around the unit circle more than one time, right? That's what we did for D. We asked someone to go around the unit circle more than one time. C and F, though, we sort of asked that in a different way. We're like, we want someone to count in this direction to get there. But for point F, we said, oh, but I want you to count in the other direction to get there. But either way, you're getting to the same point, okay? So the big takeaway from this particular diagram is like, yes, we can plot these points and that's great. And how can we write more than one way of directions to get to the same point, all right? So if we have polar coordinates, okay, one thing you might have noticed, maybe, from the what's new is we had polar coordinates, but then we had these like rectangular coordinates or something that looks more like an XY situation, okay? So I do want to label this here before we move on. We actually have an R comma theta turns out we can call it like R comma theta, but we can do a little bit of work and say, this is what it would look like on the Cartesian or the rectangular coordinate, right? And this example does the same thing here. We have an R theta and it equals some xy. In this one, we have R theta and it equals some xy. Okay. So for every point that you draw, you can draw it using rectangular coordinates, or you can draw it using polar coordinates. All right. And so that sort of leads us to this question of like, well, if they can both plot points, what's the relationship between them? Or like, how do we convert back and forth? This is very similar to the idea of pi over 2. Once upon a time, we used to say, oh, that's 90 degrees, right? It's a different way of measuring it, but we needed to know how to convert between the two. And so that's what this second section is all about, okay? So in the second section, here we go, we are looking at the relationship between rectangular and polar coordinates, all right? And so we have sort of two sets of formulas here, all right? Any rectangular coordinate, we're gonna call x comma y, and the polar coordinate, we're gonna call r comma theta. And if we have a polar form, okay, so if we have polar and we want to go to rectangular, we're going to use this first formula or set of formulas. Okay. If we want to go in the other direction, rectangular to polar, we would use this second set of formulas. Before we use these, I'm wondering if someone can tell me why we've written so carefully at the end here that x does not equal 0. Why does that even matter? Exactly, right? If we look at the formula, whoops, that came right before this, y over x. If I have x equals 0, right, that's something we've been talking a lot about this semester. I'm dividing by 0, and that's going to be problematic, or as Dallas says, is going to be undefined. Okay, so we do need to be really careful when we're having fractions that something maybe can't equal 0. Okay. So let's go ahead and convert. All right, we've got a couple examples here on converting in both directions. All right, and so example 3 here says convert 3 comma pi over 6 into rectangular coordinates. All right, and what I want to do real quick is sketch a quick picture so I kind of know like what numbers I'm looking for at the end. And so I'm not going to be fancy and draw the whole, all the circles, but I'm wondering if you can tell me what quadrant 3 comma pi over 6 is going to be in.
The first quadrant.
It's going to be in the first quadrant, precisely. So I know pi over 6 is maybe here somewhere, and I'm going out 3 circles-ish. And so we know that this is located in quadrant 1. Okay. Now we have polar and we want to get rectangular. So we're going to choose to use this first set of equations to help us out. Okay. And so we're converting polar into rectangular. We just need to know what's our r and what's our theta. Okay. And so r in this case is going to equal 3 and theta is going to equal pi over 6. Once I have that, if I want to find x, I'm going to say x equals r cosine theta. X equals r cosine theta. I'm going to plug in what I know. So 3 cosine pi over 6. How do we finish the problem? Convert the cosine. Be a little bit more specific in your language. What do you mean by convert? Okay. So I think maybe a better phrase for that, we're not actually converting anything, but this might be like evaluate cosine of pi over 6, right? Yeah, we're going to choose the coordinate that it goes with, which in fact is root 3 over 2. So we have 3 times root 3 over 2, and we could write that as 3 root 3 over 2, right? So this gives us our x coordinate. Now let's go ahead and find the y coordinate. Y equals r sine theta. So we're going to sort of play a similar game. We'll have 3 times sine of pi over 6 this time. And so now if we evaluate sine of pi over 6, what do we get? Yeah, we're going to get 1/2. And so we're going to get 3/2 for our y coordinate. That means my answer is going to be the x coordinate times the y coordinate, or sorry, x coordinate comma the y coordinate. Both of these are positive, which means it's going to be in the first quadrant. All right. So we want to make sure at the end that like our solution matches our original question, right? And so that's how you move from polar into rectangular. Are there any questions about example 3 before we move on to going in the other direction? All right, so let's try doing this in the other direction now. All right, so we're going to convert from rectangular into polar. All right, so we have rectangular coordinates and we're trying to go to polar coordinates. Okay, now that's the first part of the question. Let's do that. And then we're going to tackle the second part, which is find 2 other pairs of polar coordinates that describe the same point. All right. So in other words, after we convert it into polar, I want us to give it some different names that still get us to the same location. Okay. So if we do a quick sketch again, just to make sure we know what quadrant our final answer is going to be in. What quadrant is -1, 3 in? Yeah, we're going to be looking at quadrant 2. And so -1, root 3 is going to be somewhere in there. All right. Now, to find out exactly where it is, let's set ourselves up. All right. So just like last time, we said, oh, these are the polar coordinates. This is my r, this is my theta. But this time we want to say this is my x and this is my y. All right. Now let me zoom in for a moment so we can take a look at that formula that we need. All right. So we have r squared equals x squared plus y squared, and tangent theta equals y over x. So r squared equals x squared plus y squared, and then tangent theta equals y over x. So let's plug in the values we have. R squared will be -1 squared plus root 3 squared. Right? Do a little bit of mental math for me. What does r squared give us?
Or
It does give us 4. Excellent. Now, one of the things that would be so easy to make a mistake here is to say like, oh, what if we have -1 and we square it, but we forget the -1 is in parentheses, right? So you really do want to double check your arithmetic there, but we should get +1 plus 3 gives us 4, right? Now here's another place where things tend to go wrong. What did I do wrong here? Great, that plus minus, right? I'm taking a square root, which means I have 2 possibilities here, a +2 and a -2. And so I need to be really thorough in writing that out, okay? All right, now that we found our radius, let's go ahead and find our theta. So tangent theta equals √3 over -1, right? I know the tangent's not on our unit circle, right? So this is the one where we have to do a little bit more work to find out that angle. But what angle is theta if the tangent is -√3? All right, looks like we've got one suggestion of 2 pi over 3. Anyone else have a confirmation or a different idea for that? Okay, great. It is indeed 2 pi over 3. Okay. And so if we wanted to write one coordinate for the one that matches -1 comma √3, we could write 2 comma 2 pi over 3. Right? Just like the beginning questions, I would go to 2 pi over 3, which is right about here. And then I would count out 2 circles and I would get to the same place as my rectangular coordinate. So this, I would say, is maybe the most straightforward answer. But I want us to find 2 other pairs of coordinates that would get us to this same point. All right. Take a moment and think about how else you would tell someone to get to this quadrant. When you think you have an idea, go ahead and pop that into the chat, or you can just unmute yourself.
do we do -2?
Okay, I like that idea. If we want to choose -2, what would we choose for our angle here?
It would still be 2 pi over 3.
Okay, let's write that down and let's see. All right, so if I had this direction, that would mean go to 2 pi over 3, right, which is here. But then I wouldn't be counting up, because if you said -2, that would mean I count in the downward direction. That makes sense?
Yeah.
Okay. So if we want someone to go in an opposite direction, maybe we tell them to go down here first, right? Whatever angle this is, and then count -2 in the opposite direction. So I love the idea of the -2, but I think like Dallas has suggested, maybe we change that to a 5 pi over 3. Okay. Now I'm going to pause here for a moment. I'm going to scroll back up to one of the ones with the circle so we can actually see this. Okay. So keep in mind -2, 5 pi over 3. So -2, so 5 pi over 3 is, we're not there yet, is down here. And then if I count 1, 2 in the other direction, I do get to 2, 2 pi over 3. Okay. All right, so I would agree that one way you can say is go to a different angle and then go in the opposite direction. What's another way that I could tell someone to get to the same value? All right, so maybe something where we're like, go around the unit circle more than one time. I like that. 8 pi over 3. And so this is very much like Casey was saying earlier, how that 9 pi over 4 is actually the same thing as pi over 4, right? How would we give someone directions if we wanted them to count in the opposite direction? Nice. So we could say, go to -4 pi over 3. We're counting angles in the other direction. And we're still going 2 circles out. Yeah. And I know this is more than 2, but just to kind of reinforce the idea that there's actually an infinite number of ways that you can tell someone to get to the same point. Okay. But I like the strategies that were highlighted here. And so maybe if we were to write those down, we would say sort of like opposite angle and -r. I think this second one that Dallas suggested might be like same r, but more than one time around the unit circle. Right? That's a good strategy to have. And then this last one, we could say same r, but negative theta. Right? Now, one of the things I noticed in looking over the last exams reference sheets is I noticed that a lot of folks put like formulas down, which is great. That makes sense, right? You want to be prepared, you're going to put the formulas down. One thing I would encourage some of us to do is just double check and make sure those formulas are right. Because if you have the wrong formula here and then you use it in the wrong way, you know, then we got to do a little editing in terms of our reference sheet and make sure that's correct. Okay. But the other thing I wanted to point out was that some of us are just writing these down and maybe not the other parts. And then we're not quite sure which one to use. Okay. You can 100% write this whole thing, right? The formula and when to use it, the other formula and when to use that. All right. You could also write down some of these, like here are some different ways to get more than one coordinate. That's absolutely fine. Okay. But as we sort of move into Math 150, I want us to be really thoughtful about like what's beneficial, what's not. All right. And I think for some of us, it might be helpful to have a little bit more wordage on here and in making sure that like it's actually a helpful reference sheet. Okay. So I actually want to take a break here before we finish up this section. All right. But just to kind of give us a preview, we were just converting coordinates. But now when we come back from break, we're going to be converting entire equations. All right. And so when we come back, the thing I really want us to focus on is strategies. Like, how do we know for different kinds of examples what methods to use? Okay. So let's take a break right now. Let me pause this recording. Great. All right. So before break, we took a look at polar coordinates and converting between polar and rectangular equations or coordinates. And now we're going to take a look at, in particular, converting between polar and rectangular equations. All right, so that would be the key difference here. But we do actually use the same exact tools that we used for converting coordinates. All right, and so we're still going to have x equals r cosine theta and y equals r sine theta. And that we will use when we're looking to go from polar to rectangular. And then separately, we have this expression, which helps us go in the other direction, right? So going from rectangular to polar. All right. So like I said before break, a lot of this is about the strategies, okay? So in the same way that we approached trig identities, and we were really thoughtful about how do we know what to use, right? When we have just the one tool that's supposed to work for all the problems, it comes down to how we use that tool, not just, here's a formula, plug it in, and we're done, okay? And so this kind of thinking is going to be something we use a lot in Calc 1 in the spring. And so it's a really big reason why I'm trying to highlight that idea of decision making and strategies, okay? All of this is like pre-training for the main event, which is our Math 150 class. And so for example 5, all right, we have a rectangular equation, and we're trying to find the polar equation that is the same thing. And so I'm wondering, based off of what we have up here, first of all, do we want to use the yellow set of equations or the pink set of equations? All right, and what tells us that we want to use the pink set equations? I would agree. Yeah, exactly, right? That we're looking for the word polar. So if we want to find the polar, we want to choose the equation that ends in polar, right? It gives us, spits out a polar equation. All right, so we have x squared plus y squared equals 9. And at the end, we want an equation with what letters? Yeah, at the end, we want an equation with r and theta, okay? And so we have a polar equation we're looking for. That means at the end, we should have r's and thetas, okay? It also means we should have no x's and y's, all right? So with r and theta and without x and y. Okay. Now, I wouldn't expect you to write this out here, but I would expect it to be a thought that you think of, like, okay, what should my answer look like? It should have r's and thetas, but what should it not have? It shouldn't have any x's and y's, okay? And I think sometimes that helps ground us in what we're actually trying to find. And so all of that being said, what ideas do people have here? Ooh, r squared equals 9. All right. How did you get that? This is the equation of the circle, but how did you get that from this pink equation? All right, let's unpack that process just a little bit.
Well, looking at it, the first part of that equation is r squared equals x squared plus y squared. And
Mhm.
so there you have the x squared plus y squared. And then 9 is a square. And so you just break it down.
Okay. And so one thing I heard that I really liked was that we have this x squared plus y squared, right? We have that in our equation. Everywhere we put in x squared and y squared, or C1, we can replace it with r squared. So r squared equals 9. And all we did was, just didn't leave myself enough room. Was substitution. Okay, so everywhere we saw the x squared plus y squared, we replaced it with r squared. And now when we isolate r, what do we get? I'm going to give you a no on that. There we go. Now we got a plus or minus 3. Okay. And so what we have here is that if we go into wanting to graph a circle, right? And I love that this was brought up earlier. This is the equation for a circle in rectangular land. X squared plus y squared equals r squared. But this r equals plus or minus 3 is the equation for a circle in polar. Whoa, that's not how you spell polar. In polar. Okay. So you can use this equation to describe a circle in rectangular land, but if you were in polar land, you could just say r equals 3 or r equals -3. And that would give you the equation for a circle. Okay. Now imagine you had to do a whole lot more algebra, and this was in the middle of a way bigger problem. You could work with a lot of letters and a lot of numbers, or you could work with r equals 3. I bet when you're in the middle of that problem, it's going to be way more helpful to think about something with fewer letters, fewer numbers to deal with, okay? And so the equation of the circle, not so easy to write in rectangular land, but way simple to write in polar land, okay? All right, so that's one example, all right? Let's do a couple more. And then let's take a look at maybe some of the graphs and how we can use Desmos to help us out, all right? So for example, 6, not 5, you already did 5. For example, 6, it says find the polar equation for x squared plus y squared equals 6y. Should we still use the pink set of equations for example 6? I agree. That is a yes, right? For the same reason Dallas gave earlier, which is it has us looking for polar equations. So we want to use the one that ends in polar equations, right? But compare these two equations for a moment. What's the same and what's different?
We're still using the x squared plus y squared, but now we have another like letter y.
Exactly, right? So this left-hand side is exactly the same. The right-hand side, though, 9 and 6y, that's a little bit different, okay? And so when we think about our strategy here, I bet we can use the same strategy on that left-hand side, where instead of writing x squared plus y squared, we can write that as r squared, right? And so we're doing a substitution here, right? If I left the right-hand side as 6y, I don't think we could achieve our goal here of we want an equation with r and theta, but also no x's and no y's, right? So how do we get rid of this y here? What are some ideas we have? So you want me to just write this? Maybe. Okay. So that's one suggestion, right? Maybe 6y is the same as 6 theta. What would that mean if you just wrote 6y equals 6 theta? What would that mean about the relationship between y and theta? Well, I think if I saw something like this, that would imply to me that y is the same as theta. Right, 6y equals 6 theta, then y equals theta. But I don't think that that matches the relations that we have up here. Right. But take a look at what we have here. Right? I argue that we have enough information on this page to figure out how to get rid of the y. No more y's, only thetas and r's. So if you think you have an idea, you could like put it in the chat or send me a direct message. Oh, okay. Y equals r sine theta. Where did you see that? In the yellow one. Okay, so like right up here, we have y equals r sine theta. I would agree that that's actually going to be helpful for us. And maybe we sort of put a little yellow bubble around that, because it turns out we're going to be able to use both depending on the context. Okay. So we have r squared equals 6, but instead of y, everywhere we see a y, we're going to write r sine theta. So 6 r sine theta. Okay, and this comes from our yellow y equals r sine theta. Okay. Now, how do we rewrite this equation? In other words, how do we sort of solve for R? All right. I'm so glad that you said this. This was in fact something that I've seen on quite a few homeworks that is a big, do not do this. So I've seen people divide by R and they get R equals 6 sine theta. Why is that a problem? Okay, I would agree with Ian that we actually want to move that 6R sine theta to the left and factor. But why is what we have written here incorrect? Maybe if we keep writing what Ian has suggested, factor out the R. What do we do from here? I know this process is sort of like autopilot for some of us, but I want us to know like why the thing in the red is incorrect. So let's focus on just this piece for a moment. How do we solve for R? Set the factors equal to 0, okay? So we get R equals 0 and R minus 6 sine theta equals 0. Let's leave ourselves a little bit more room here. Right, so I get R equals 6 sine theta. That's what Dallas has got though. He got R equals 6 sine theta. So why am I like writing this suggestion in red? Okay. I boxed off this answer, but you know what I left off? The R equals 0. Okay. What happens on a lot of situations where you divide by something, you end up getting some of the solutions, but you lose some along the way. All right. And so this is definitely a learning moment, I hope, for folks, because it's a great example of a place I don't want to see folks lose points. I don't want to see you lose solutions because it's such a common thing to do, but I want us to be like, nope, we are aware that this is a thing. I'm going to ignore my very strong instincts to divide by R to get things as simple as they can, as fast as I can, and buy into the idea that if we do that, those shortcuts, a lot of times we lose solutions. And so in this case, we would really need to bring everything over, set it equal to 0, and then factor, okay? Now we do need to unpack what these solutions mean, right? So I said, find a polar equation for x squared plus y squared equals 6y. It turns out that this is, if we graph it on Desmos, if we graph R equals 6 sine theta, we will get the same thing as if we graphed x squared plus y squared equals 6y. However, if we graph R equals 0, we will not get x squared plus y squared equals 6y. what will we get if we graph r equals 0?
Center?
Yeah, we're just going to get a single point at the origin. All right. So I know I just made a really big deal about, I don't want to see you do this. Don't divide by r. And now several minutes later, I'm like, that one wasn't actually a solution anyway. But in a lot of those trig equations ones, precisely on our exam or maybe on the homeworks, that was a mistake I saw quite a bit. So sometimes, like in this case, it didn't really matter at the end result. But sometimes in other questions it does. And so I just want us to be really aware of that. If we go the safe way, we'll always be able to get to, okay, this one is not a solution and this one is, and we'll make sure that we get all of the solutions. But in other cases, if we shortcut that step, we're going to miss a bunch of solutions along the way. Okay. I do want to see in your work the factoring. All right. I do want to see this, and I want you to tell me why one of them's not a solution. Right. All of these show that you know more than just the procedure, that you know how to simplify these equations and convert these equations, and that you understand why some of them don't give us solutions. Okay. So more layers that I'm looking for here. All right. Are there any questions on example 5 or 6 so far? All right. Let's go ahead and take a look at this last example here. Find the polar equation for y equals 3x plus 2. All right. And I'm going to ask you to go ahead and tell me what strategies you think we should use. How can I get this to be an equation with only r's and thetas? Change the x and y to the yellow ones. Okay, so let's see. The y was r sine theta. The x's were what? What did we write for the x's in the conversion? R cosine theta, exactly, right? So we've got our r sine theta, our r cosine theta plus 2. Nope. How come that has a plus 2 at the end? I know it's not loading on the screen. There we go. How come there's a plus 2 on the end there? And how come there's a 3 in front of that cosine? Yeah, right. This 3 is 3x. So if I want to replace x, I still have to keep the 3. And there's still a plus 2 here. So I still need a plus 2 there. Right. And I'm only pointing that out, not because I think that's a common mistake, but sometimes when we're moving too quickly, we just forget to write out the whole thing that we're substituting, right? And some of us, I know we sort of do some work over here, then we do some work over here, and then we put it all back together. And sometimes in that, we lose parts of our equation. So I would really encourage you to just make sure that you know how to make that substitution in an accurate way, okay? But at the end of the day, what we want to do now is we want to get R all by itself. And so that's where I'd like a lot more from you folks. How do we get R by itself from here? I know we've never seen this particular question, but we've seen a lot of situations sort of similar to this. How do we get R by itself?
How do we divide by sine theta?
Sorry, say that again. Divide by sine theta.
Yeah.
Okay, so let's see. If we divide by sine theta, we get R equals 3R cosine theta over sine theta plus 2 over sine theta. What do we do after this to get R all by itself? Yeah, right. We divided, we got R equals, but we still have a little R hanging out in there, right? It's like a 3R cosine theta. So we still have an R in there. All right. So valid guess, right? You have R sine theta. I'm going to divide the sine theta away, get that R by itself. But we have more than one R. What do we do about that? Okay, so let's try that. If we move everything, so this was sort of option 1, right? Option 2, we're going to move everything to the left and factor. So we get R sine theta minus 3R cosine theta minus 2 equals 0. And what should we factor? Okay, so I moved everything to one side, but when I look at this left-hand side now, I don't see a common factor, right? So let's try that other suggestion. Maybe we just move the 3R cosine theta and leave the 2. Okay, what's the benefit in that? What happens when we leave the 2? Okay, we don't have to factor it, but what does it allow us to do? Like, what can we factor out on this left-hand side? Yeah, now we can factor out an R. And Ian, I'm so glad you said that, because that is exactly when you suggested move everything to one side, set it equal to 0, right? It's the same strategy we used up here, except now we're just being a little bit more clever, right? So I can see that thinking where Dallas is like, well, let's just do the same thing. Let's move everything to one side, set it equal to 0, which was option 2. But turns out that that was actually too many things because we weren't able to factor out what we wanted, okay? And so I want us to maybe think about this last question a little bit like a Goldilocks situation. So I don't know how many of you know that that kid story Goldilocks and the 3 bears, but basically this girl like breaks into these bears' house, right? And is like eating their food and sleeping on their beds, all sorts of things, which really were probably not okay. But taking that and saying, you know, she's like, oh, this bed is too soft, right? This one is too firm. And this one is just right. Or when she looks at the oatmeal and she's like, this one is too hot, too cold, but just right. Right. And so sometimes we need to think about all of the tricks we've ever learned and sort of split them a little bit and say like, well, in the past, I just divided by it and that was fine, except I had another R. And so that was a problem. And so, well, let me try the trick where I move everything to one side and set it equal to 0, but oh shoot, that's too much. I can't factor now. And being patient and being like, what if we just move the things we want to move? Let's just move the things that have the R. Great, because now what we can do, right? So let's put a green smiley face over here. What we can do now is factor out the R. We have R in parentheses, sine theta. I'll let the screen catch up. Sine theta minus 3 cosine theta equals 2. How do I get R by itself? Great. Let's divide this clump away. Clump being a very mathematically accurate term, right? But we get 2 over sine theta minus 3 cosine theta. And that, my friends, is if you wanted to plot y equals 3x plus 2, what shape is this, by the way? If I said graph y equals 3x plus 2, that's a line, right? Turns out if you want to write a line in polar, it's a lot more complicated. So that's why up until now, graphing lines, we've used y equals mx plus b. It's a lot more straightforward. But in a similar way, we didn't really introduce circles. We didn't really introduce circles into the curriculum until later because those equations were a little bit more complicated, but it turns out the polar way of describing circles is a lot more streamlined, okay? So it has its benefits. Polar circles, super, super straightforward equation. Polar line equations, not so straightforward. Okay, so we sort of pick and choose which kind helps us in a way that is like easier to understand. Okay. All right, so what I want to do here, I think, okay, let's do this. I'm going to hop on Desmos real quick. Great. Okay. So we've used Desmos for a lot of things, right? We've learned how to like graph equations, find solutions, blah, blah, blah. We know how to do radians versus degrees. Anybody remember what button helps us find the radians or degrees choice?
The tool button?
The tool
like
button.
The wrench, yeah.
So I'm going to touch the tool button right here. And one of the ones that I don't know if you've seen this and maybe just been like, I don't know why we're not using it, is in the grid portion. You see how we have like the one that's in the green, but look at the one right next to it. If you click that one, now you're in polar. So Desmos can not just graph in rectangular coordinates, but it can also graph in polar coordinates. Okay. And so let's go ahead and try graphing some things. Let's try 3. Oops. Nope. Let's try R equals 3. That was what we said that circle was, right? R equals 3 is a circle with radius 3. Okay. Can someone read for me what we have in example 6? What equation did we end up with in example 6?
R equals 6 sine theta.
So 6. Oh, I don't know where the theta is here. Oh yeah, you just type it. Okay, so I've got these here. So if I just show the blue curve, right? R equals 6 sine theta is a circle that is like a little bit above the x-axis, right? So keep that picture in your mind. I'm going to go back to rectangular. I'm going to ask someone to tell me what the original rectangular equation was for this, okay? I'm going to go back to the wrench. I'm going to click on the rectangular one, the one that we know, tried and true. All right, so let's go back into here. Let me get a new line. What was that equation we had for the original one in example 6? Great, thank you. So we've got x squared plus y squared equals 6y. And that's the purple one, right? I think you can choose your colors if you want a different color. Like I could choose it to be green, if that's easier to see. But this green circle and the blue circle are exactly the same. The blue circle is what we called it in polar, and the green circle is what we called it in rectangular. But if I graph them both at the same time, you only see one circle because they're literally right on top of each other because they're the same graph. Okay. And so as you're looking at your polar equations, if you wanted to like think about how do I convert these, you can do your conversion and then you can graph them on Desmos. And if you get the same graph, then you know that your answer was correct. Okay. All right. So cool new features on Desmos. One of the quizzes that you'll do this week is actually involving Desmos. It's not in the Desmos classroom, but it's an assignment on Canvas. And so you'll be going through and like figuring out how to graph in polar, but that wrench and then going to the circle-y grid situation will be really helpful in sort of setting that up, okay? All right. Now on your own time, if you're curious, you can graph y equals 3x plus 2 and graph this. Just make sure that fraction line goes across the entire bottom. You should get the same line there. All right. So let's take a look at equations that ask us to go in the other direction now. Okay, so in particular, let's look at example 8 over here. It says find the rectangular equation for r equals 3 over 1 minus 2 cosine theta. Okay, so what are our thoughts? Tell me some strategies and let's try them out. Okay, it's okay if it doesn't get us where we want to go, but it might help us in a different case, right? So brainstorming these strategies in general, I think, is really useful. Who's going to be brave with the first idea? Try to isolate the cosine theta. Okay. All right, so if we did that, we could get, let's see. How would you isolate that? Let's talk through that a little bit more. multiply the denominator. Great, so we get r times 1 minus 2 cosine theta equals 3. All right, what would we do from there? And thank you, by the way, for being brave and putting an idea out there. All right, this is very similar to a question I asked most of us on the group exam. I was like, you have something and you've got parentheses, what do you do? And pretty much everyone was like, oh, you distribute, right? So that's like a structure that we're used to seeing. We just have different letters here now. So we get r minus 2r cosine theta equals 3. Great. How do we keep going to get cosine theta by itself?
And add to our cosine to the other side.
Say that again, Ellie.
Add to our cosine. Oh my God, I forgot the r is also in cosine.
Yeah, r is in both, right? But maybe one thing that we should sort of write for ourselves is we want an equation with x and y and without r and theta, right? The fact that we're looking for a rectangular equation means at the end of the day, we better have x's and y's. We don't want to have cosines and sines and r's. Okay. So I could imagine if you were working on this problem and you didn't read it very carefully, maybe you would get to this step and you would be like, great, let me factor out my r because that's what I do. And then you would be like, oh my gosh, I'm back exactly where I started. Right? Which happens. It happens to all of us. I was working on a take-home test this weekend and it happened to me. I like did this problem and I was going through and then all of a sudden I was like, oh my gosh, this is where I started. Right? And so we want to be really careful about that because just because this is every time we see a bunch of things on one side with the same variable and we factor it out doesn't mean that's the right step to have here. Okay. That's why we have erasers and all is well with the world. But I noticed something in the chat that says convert r cosine to x. So we might notice we have an r cosine theta here. Right? And if we go back to that list of formulas, everywhere we see an r cosine theta, we can replace that with x. All right. So I'm going to say we're not converting anything, we're substituting maybe. All right. But we could write this as r minus 2x equals 3. All right. Well, I feel like this is a step in a good direction because we want x's and y's and we don't want r's and thetas. So we've gotten rid of the theta. How do we get rid of the r? All right, so your suggestion would be this. And what you're telling me here is that r equals y. Okay. Is that a true statement that r equals y? Because if we go back up here, right, let's kind of scroll up for a moment. I don't think we have anything that says r equals y. I mean, life would be nice if we could do that, but that's not necessarily. Okay, so let's see. Another suggestion, what if we made r? So instead of y equals r sine theta, all right, let me write that down here. Where did it go? Not true. But another suggestion might be r equals, oops, y equals r sine, oh my gosh, theta, and then we could solve for r. Okay, so if we substituted that, that would give us y over sine y over sine theta minus 2x equals r. So that's a true substitution, right? Like it's true in that it's mathematically accurate. Does it help us? Yeah. I would say it kind of does. Like we got a y now and we got rid of the r, but then now we have a theta. Yeah. Okay. So I would say in a better direction, right? The same idea, but yes, what else can we call r? Well, we know r squared equals x squared plus y squared. And Dallas is correct. R equals the square root of x squared minus y, plus y squared. Okay. Well, let's try this idea. Everywhere we see an r, now we're going to put square root of x squared plus y squared. We have the minus 2x from before equals 3. Okay. True substitution, like mathematically accurate. Do we have any r's and thetas in here? I don't think so. I think we got rid of them all. Do we have an equation with only x's and y's? We sure do. It's an ugly equation, but it's an equation with x's and y's and without r's and thetas. Okay. This is what we call an implicit formula. Right? And we call it implicit because it's not a y equals equation. Okay. Could we solve for y? Absolutely. But we don't have to. The only thing we need to do is get an equation that has x's and y's and doesn't have r's and thetas. This fulfills those requirements. So this is an acceptable answer. Okay. I do want us to walk through how to get y by itself, only because I've seen some sort of questionable algebra things going on. And I want us to spend a little time sort of like thinking about some of those fundamental algebra situations. Okay, so to solve for y, let's write out what it would look like. Square root of x squared plus y squared minus 2x equals 3. All right, so let's focus on this piece for right now. How can we start to get y by itself? All right, let's talk through some legal as well as illegal moves. All right, plus the 2x, I buy that. X squared plus y squared equals 2x plus 3. Wonderful. All right, what next? Okay, so if I square both sides, what do I get on the left-hand side? Great. What do I get on the right-hand side? All right. These mistakes, folks, cannot happen anymore. All right. This is going to cause some big problems when we get to calculus. It's so tempting. It's so tempting. We got to foil. Okay. We got to foil. So instead, we would say 2x plus 3 squared. Okay. This is totally fine. But we have to know that the thing with the red X through it and the thing in the green box are not equal to each other. Okay. In fact, let's write here that we must FOIL. All right. But imagine that we just had x squared plus y squared equals this squared. I bet you can tell me in 2 steps how you're going to get y all by itself. Right, so how do we isolate y here? All right, subtract that x squared. Y squared equals 2x plus 3 squared minus x squared. Great. Last step to get y all by itself. Sorry, I know my screen is lagging a little bit. Yeah, we're going to square root both sides. All right. Let me give the screen a moment to catch up. There we go. Okay. How many solutions do we end up with? Great, because when we square root, we better have that plus minus there. And we better have this. Okay. How many times do you think I've seen this as an answer? We have this, and then we simplify, and we get that. Way too many. So many times it makes me super sad. How come we can't do that? Yeah, this minus sign in here, if that minus were a multiplication, we'd be good to go. But it's not a multiplication. And so when we're adding and subtracting, we have to be really careful, because just like we had to FOIL, we would have to like unfoil here, if that makes sense. Okay. This line right here, we call this one the implicit formula. This one we can call the explicit formula. All right. All that means is explicit, we got y all by itself. Implicit, we were like, that's not really the point of the problem, so we're going to leave it here. Okay. A lot of times when you get into like higher and higher math, it's okay to have implicit situations because the purpose of the work is a lot of the stuff that came before it. It is important though, particularly for those of you who are like, I keep losing points for this illegal algebra stuff and I don't know why. This is a great place to do a little bit of extra practice for yourself to sort of avoid those mistakes. I'm not going to force you to do them, but if you continue to make the same mistakes, I'm also not going to feel super bad for you. Right? So like at this point in our math careers, a lot of times these are the little things that make calculus just like super, super hard. But if we have a good foundation there, it'll make our lives a little easier. Okay. I'd like to take a look at one more example here. All right. And this one, we are going to go ahead and leave in the implicit formula solution. Okay. We have to find the rectangular equation for r equals sine of 2 theta. All right. What are some ideas here? How are we going to get this equation to have only x's and y's and no r's and thetas? All right, got double angle identity. I love it. So if we were to use a double angle identity, we would get r equals 2 sine theta cosine theta. Love it. All right. That's great. We still have r's and thetas though. So what next, right? It's okay to have a one step in the right direction, but then know that there are going to be other steps later on. Like that's okay. Square both sides. Can you tell me why you want to square both sides? I like the idea. Oh, okay. So if we squared both sides, we would get r squared equals 2 sine theta cosine theta squared. Ah, okay. So where do you see the Pythagorean identity coming into play? Okay, so we have r squared equals 4 sine squared theta cosine squared theta. All right, now tell me more about this distribute the r situation.
I'm just going to use my mic. I was thinking because with the R just by itself, it would kind of be a little difficult to do anything besides for maybe division. So if we had like included an addition sign or a subtraction sign, then we could FOIL and then we could move it to the other side and then hopefully get R to be on either cos or on both sine and cosine.
Okay. So I love this idea that like, if we had an R on this side, on my screen is still being a little slow, but if I had an R on the right-hand side, that would definitely be helpful, right? Or if we had like sine squared plus cosine squared, that would be helpful. Then, so those are all great ideas, but if we don't have them, right, we can't just like introduce plus and minus signs into there, right? But I think a really good like first step and second step, and then realizing maybe this isn't getting me where I want to go, okay? But as a reminder, like at the end of the day, what do we want to have in our equations if we're changing it to rectangular form?
X and Y.
Yeah, we want X's and Y's, right, Ellie? We want X's and Y's. And so all of this work here that we were hoping to do is still keeping us with R's and thetas. And so I wonder if we can revisit one of the ideas that Dallas brought up, which is like, if only this were not sine theta, but it was R sine theta. Okay. So if I made this, what would I have to do to the left-hand side to make it still be the same statement or a true statement? Great. Okay, so what do I get on the left-hand side then, Matt? Wonderful. Okay. You know how sometimes I say we like have a fancy one, right? We're multiplying by a fancy one. I call this clever multiplication. You're going to do the same thing to both sides of the equation. You didn't change anything, but what you did is you made an R sine theta where you wanted an R sine theta. Okay. That means everywhere I see the R sine theta, I can put Y. So in other words, R squared equals 2Y cosine theta. All right. Well, we're heading somewhere. We're heading somewhere where now we're getting, at least we have a Y. What are our thoughts for maybe what could come next? Okay, times R again. So if we use clever multiplication again, right? On the left-hand side, we're going to get R cubed and we get 2y R cosine theta. Now I can write the R anywhere I want to, but I'm choosing to put it right next to the cosine to make it real clear to me that now I'm going to want to do a substitution. And when I make this substitution, I get R cubed equals 2yx. All right. So this is a new strategy. I don't think we've ever seen something like this before where we multiply both sides of the equation, right? We've mostly multiplied by 1 or like added 0. But now we're saying, well, as long as we adhere to this basic algebra rule that if we do something to the left-hand side, we also have to do it to the right-hand side, then we're still good. Okay. What do we do now? We've got X's and Y's on the right-hand side, but we still have some R's on the left-hand side. Ooh, okay. Before we do this, all right, so in the chat, Dallas just typed maybe R times R squared. Can someone else tell me what might be going through his head right now? Why would he want to have an R squared? Wonderful. I love it. Love it. All right. So if we cleverly split into R times R squared, we can do exactly as Matt suggested. Everywhere there's an R squared, we're going to put X squared plus Y squared. Great. Love it. So split, sub in. All right. We've got less R's, right? Before we had R cubed and now we just have R. How do we get rid of that last R? Oh, nice, nice. So the one where we had said from a while ago, or actually in the previous problem, if I just have an R that I want to get rid of, right? I can't just like make it what I want it to be. I have to be true to the relations that we have here. And R equals the square root of X squared plus Y squared. So I'm going to go back down here. I have the square root of X squared plus Y squared times X squared plus Y squared equals 2YX. Have we achieved our goal? A rectangular equation that only has X's and Y's and has no R's and no theta. We have. Would we call this an implicit or an explicit formula that we have here? Yeah, we would call this an implicit one, right? Implicit formula. Implicit because we didn't get Y all by itself. We could, but it's kind of a lot of work. And this, all this ink up here, that's where I want our thinking to be. Okay, I want us to be thinking, how do I get rid of this R? How do I get rid of this theta, right? And thinking about the tools that we have here. I'm so glad that we were like, double angle, we know this one, we've seen this one a lot, right? And then talking through some other ideas that didn't end up helping us actually helped us come up with how to get started on that first line there, right? And that was something that I heard in some of that conversation during the group portion of the exam. It was like, well, let's try this, let's try this. Well, maybe we should actually try it this way, right? And that kind of conversation is just so powerful. But this, my friends, is what we get for our implicit formula for that rectangular equation. In your own time, if you graph R equals sine 2 theta, and then separately you graph this, you should see on Desmos that they are the same exact graph, all right? But which one of these would you want to work with in the context of a bigger problem? Probably just a smaller one, something a little bit more simple, Okay, and that's precisely how you're going to be using it when you look at polar equations again in Calc 2. Okay. And so I think this is a good place to stop. So I'm going to go ahead and stop the recording.